change. Again, this is something you should have done in elementary school. But very quickly, physical changes can be reversed generally. Chemical changes cannot be reversed or are difficult to reverse. So we did an experiment in which we had a salt, I don't remember, it was a copper sulfate or something that had some associated waters with it. It was a hygroscopic chemical that had absorbed a lot of water molecules, and we essentially boiled the water off. That was a physical change. We were just boiling the water off and leaving that copper sulfate or whatever by itself. Okay? Boiling water off is a physical change. We added water back to it and it changed instantly back to what we had started with. It was easily reversed. So we didn't really change the nature of the chemical, right? Another physical change is melting, boiling, all those, sublimation, what have you. Chemical change is an actual rearrangement of the atoms and molecules in a substance. So cooking, when you cook something like eggs, you're actually denaturing the proteins in the eggs and breaking apart some of their bonds and rearranging those molecules. So you cannot uncook an egg, right? That's a chemical change. It can't be reversed. So we have, for physical changes, we can plot these melting and boiling, these physical change points. So the heating curve always looks something like this, where we have our three phases. The coldest phase, this is increasing temperature. The coldest phase here would be the solid, right? The medium phase is the liquid, and then the hottest phase is the gas. Now when we go from a solid to a liquid, this period here, this is melting. This phase here, when we go from a liquid to a gas, this is evaporating or boiling. Okay, so this is stuff you know already. You know that when you boil water, it turns into a gas, or when you freeze it, it turns into a solid. It's just putting it on a graph, so it looks a little bit different, but you should be familiar with this graph and where everything goes on it. And then, so for water, the melting and freezing back into a solid would be 0, right? And the boiling is 100 degrees Celsius. So this would be water. What was I going to say? You should be able to go between Celsius and Fahrenheit. The formula will be given. You just need to be able to do the math for that. Do you want me to review that? The math. There was something else I was going to say with regard to heating curves, but I can't remember now. Oh yes, the kinetic theory of matter. What is the kinetic theory of matter? I'm going to answer for us. Kinetic theory of matter says that atoms and molecules are in constant and random motion. And this is going to be really important when we study gases. But for now, just know that atoms and molecules are in constant random motion. As a solid, those molecules and atoms are vibrating in a solid, in a liquid, and in a gas. They vibrate the least in the solid form, a little bit more in liquid, and the most in a gas. And in a gas, they're always like colliding with each other randomly. Okay? So, let me see if there's anything else in this chapter. Oh yeah, we have our, I guess I'll do a real quick conversion from Celsius to Fahrenheit. So we said water boils at 100 degrees Celsius. What is that in Fahrenheit? Well, we have our equation. Degrees Fahrenheit equals 9/5 times the degrees Celsius plus 32. So we know our degrees Celsius, we can plug it in. And you can pause it and try this on your own if you want to. Degrees Fahrenheit equals 9/5 times the degrees Celsius, so we'll plug that in, plus 32. So now it's just algebra. Let's subtract 32 from both sides. So we have degrees Fahrenheit minus 32 equals 9/5. So I'm going to multiply 9 times 100. 900 divided by 5. What's 900 divided by 5? I don't know off the top of my head. 180. So we've got F minus 32 equals 180. I didn't have to actually subtract that though. F equals 212, right? So, and we know that's right because water boils at 212 degrees Fahrenheit. Okay? So you should be able to use this equation a little bit more elegantly than I did. And go both ways with it too, not just from Celsius to Fahrenheit, but from Fahrenheit to Celsius. Okay, then we have balancing equations, which is always fun. So you might have questions like this. Solid zinc reacts with liquid hydrogen monochloride to make solid zinc 2 chloride and gaseous hydrogen. In words, now you need to put it into chemistry. So it says solid zinc. So zinc, whenever it specifies whether it's a gas, liquid, or solid, you need to put that in parentheses. So solid zinc reacts with liquid hydrogen monochloride or hydrochloric acid to make solid zinc 2 chloride. So it says zinc 2 chloride. So what's the chemical formula for zinc 2 chloride? Well, we know zinc is going to be a 2 plus, that was given. Chloride is in group 7A on the periodic table, so that's going to be a 1 minus. So we'll do our switch, zinc, and then the 2 is going to go to chloride, like we did in the last chapter. So it's zinc ZnCl2 plus, and it says this is solid, plus gaseous hydrogen. So hydrogen gas, and we know hydrogen is a homonuclear diatomic. So now we need to balance this equation. Okay, so we've got 1 zinc on this side and 1 on this side. We've got 1 hydrogen here and 2 hydrogens here. So I'm going to put a 2 here. So now the hydrogens are balanced. 2 chlorines, 2 chlorines. This is balanced. Let's do aluminum. So on this one, aluminum plus ferrous oxide makes aluminum oxide plus iron. This is what's given. It doesn't tell us what state things are in, so you don't need to worry about it. Alright, so we've got 1 aluminum, 2 aluminums. So I'm just going to put a 2 here. We've got 1 iron, 3 oxygens, and only 1 oxygen. So let's put a 3 here. So now we changed something here, so we need to recheck. 2 aluminums, 3 irons. So let's put 3 there. 3 oxygens, 3 oxygens. We're balanced. Sometimes you just need to play with them. So sometimes you'll have a question that's like, what's the combustion reaction of this molecule? Now what is required for combustion? Oxygen. So whenever it says, what's the combustion reaction of this molecule? You have this molecule plus oxygen. And what do combustion reactions produce? They produce carbon dioxide and water when it's just a hydrocarbon. Okay? When it's just a hydrocarbon like C8H10, right? right? Whatever hydrocarbon, that's all your products are gonna be. But this one has a chlorine in it, so we're gonna have an additional hydrochloric acid produced, okay? But on your test, whenever you have a combustion reaction, just make sure you're adding oxygen to combust it, and then your products are gonna be carbon dioxide and water, okay? So let's balance this now. Over here, we've got 2 carbons and 1 carbon. So I'm just gonna go ahead and put a 2 here. 3 hydrogens, and look at that, 3 hydrogens. 1 chlorine, 1 chlorine. How many oxygens do we have? There's 2 on this side. 2 times 2 is 4, plus 1 is 5, okay? So that's not good. This one's more complicated because we have an odd number. We had an odd number here, but it just happened to work out. Here it's odd, so I'm just gonna go ahead and add a 2, and that will make it a little bit easier for us. So now how many, and we have an odd here, so I'm gonna go ahead and add a 2 here to make it even. And now I've got 2 chlorines, so I'm gonna add a 2 here. And let's see what we have now. So now we've got 4 carbons, right? 2 times 2 is 4. And only 2 here. So we're gonna have to put this to 4. And how many hydrogens? 6. There's 4 here, plus 2 is 6. 2 chlorines, 2 chlorines, 2 oxygens. How many oxygens do I have? 8. 4 times 2 is 8, plus 2 is 10. So I need to put a 5 here. 5 times 2 is 10 in order to balance this. Is that right? Alright, now sometimes when you're balancing equations, you might actually go a little overboard and put 4, 10, 8, 4, and 4. I was hoping that would happen today, but I didn't pick the right one. Anyways, this is still right, because it's the ratio of these molecules to each other. So this is actually right, but you can go ahead and like reduce this fraction, right? It's kind of like reducing a fraction. You can divide all of these by 2. So if you get to a point where you have something where there's a common denominator to all of these coefficients, you can go ahead and reduce it to 2, 5, 4, 2, and 2. You understand? We couldn't before because we had a 5, which wasn't divisible by the others. Okay, so really quick, we have several different types of reactions. There's single displacement reactions. Double displacement. Combustion, which again is whatever your compound is plus oxygen going to carbon dioxide and water. Okay, this is what happens in your car's engine. You're taking in oxygen and burning your fuel, which is a hydrocarbon, thanks to our oil field dads, and you're producing carbon dioxide and water. Unfortunately, you can't get oxygen to the engine fast enough, and so there isn't complete combustion. Oxygen becomes the limiting reactant in a car's engine, and so it's not able to burn all the fuel into carbon dioxide and water, and so we have incomplete combustion, okay? And oxygen is the limiting reactant in that case. What are our other kinds? We've got formation, and something's being formed, decomposition, and all of these sound like exactly what they look like, right? Their titles kind of give away what it is. Formation, decomposition, complete combustion, and incomplete combustion. Okay, and that is all for chapter 6. Stay tuned, chapter 7 is going to be even longer.